Thank you. Thanks. Hello, my name is Chad Wolf.
And I'm Chris Merkel.
And we are performance tools engineers for Apple. And this is session 412. We're going to be talking about profiling in depth. Now, today's session is going to focus on the time profiler in instruments and how you can use it to optimize your applications. The time profiler is the place to go when you're trying to figure out where your application is spending the bulk of its time. So, example. And it's also very useful when you're trying to discover what your application is doing at runtime. So you want to see who's calling what. Now our session breaks down a bit like this. We're going to talk a little bit about the motivation on why we wanted to create a session devoted to just the time profiler. But the majority of our session will be revolving around demonstrations. And we're going to show you some of the details on how the time profiler works. And we're also going to show you how your applications work below the source level. And then we're going to give you some final tips on how to use the time profiler. So quickly about our motivation. It actually comes from the creation of Instrument 7 itself. With Instrument 7, we wanted to go with a new look and feel, and that meant some new artwork. But it also meant, in order to get that new feel, we wanted it to be more responsive, and we wanted it to feel a little bit smoother. So we're going to do some performance optimizations for our UI in general. And we also wanted to try some new graphing styles. And these graphing styles were things that we wanted to do in the past, but we didn't have the performance to in our existing graphing code. So we knew that we're going to have to focus on the rendering. And this is actually a pretty difficult piece of our application, because Instruments has to deal with hundreds of thousands and sometimes millions of data points, and has to try to crunch all that down into a presentation that's both simple and easy to understand. So there's definitely some algorithmic complexities in there. And so what that meant for us is that we had to rewrite a significant portion of our application, and that is the track view that lives up here at the top of the app. So Chris and I, over the winter, we took our design for the new track view, and we started building it up out of a series of prototypes. Now, we didn't do our prototyping in Instruments itself. We broke it out into a separate application to keep it simple. And this is what one of our last prototypes looked like. Now, while we were prototyping, one of the things that we did was we set a performance budget. And as we layered on feature after feature, we were constantly evaluating the performance of our code against this budget. Now, when we found we were exceeding the budget, we would use the time profiler to figure out where in our application things were going wrong. And sometimes it was an easy fix, but sometimes it wasn't. But since we were prototyping, even some of the bigger structural changes we had to make to get the performance back on track were still fairly easy. Now, when we integrated it back into Instruments, we used the time profiler again to find the hotspots in our integration points. And after a few iterations, we had a version of Instrument 7 that was meeting our performance goals. Now, we were so thrilled with how the time profiler got us through this winter that when WWDC came up, we decided, let's create a session that talks about nothing but the time profiler and the kinds of problems that it's really good at solving. And we also wanted to share with you a little bit about our experience when we were writing the track view. So what we did this year is we created a demonstration application on iOS that looks very similar to our first track view prototype. And we set some performance targets for ourselves. Firstly, 100,000 data points is what we wanted to graph. We wanted to do a perfect 60 frame per second for both panning and zooming. And we wanted to make this all work on an iPad mini first generation. Now, we picked the iPad mini first gen. This guy knows what I'm talking about. Because we knew that it's going to work well on all of the other platforms, especially our later platforms. So now Chris is going to show you our application. He's going to time profile it. And he's going to show you some of the kinds of things that we found when we were putting this together for you. Chris?
Thanks, Chad. So here I have our prototype application up in Xcode, and I want to just call out a few things first. Our initial implementation, we discovered, can't handle even close to 100,000 data points. So initially, we're just working with 10,000 data points to get us going. And another important point is that you should always do your time profiling on release builds. You really want to take advantage of the compiler optimizations while you're profiling. So I'm going to go ahead and start profiling our application. And to do that, I'm going to, from the product menu, choose Profile. This is going to build the application, install it on the iPad, and bring up Instruments Template Chooser. Here it is. Time Profiler is already selected for me. So I'm going to go ahead and click Choose. And here you'll see Instruments and our new track view. And we'll get back to that in a minute. But right now I'm going to go ahead and start recording. Click the Record button and show you the app. Now I want to emphasize what you see here. This is not the simulator. This is QuickTime mirroring what is currently on the app. So here's our graph. I can go ahead and scroll. Well, scrolling's okay. It's not too bad. Now I'm going to zoom out by pinching. It's okay at first, and then it starts to stutter and stutter and stutter. That's pretty bad. And now finally, I'm going to just scroll back and forth with my finger. I'm actually moving my finger, but the display's not updating. It's very, very laggy. That is very poor for performance. So let's take a look at what's going on. I'm going to go back to Xcode, or Instruments, stop the profiler, and really quickly show you the new track view. Here we're seeing our CPU usage. What this is the average CPU usage for a specific unit of time, and that time depends on your current zoom level. And you can kind of see the different parts as I used my app where it was spending its time. This is the scrolling, this was the zooming out, and this was the scrolling back and forth while zoomed out. So one of the nice things about the new track view is I can go ahead and just use a pinch gesture to zoom in on a piece of data that I'm interested in. If you're not using a trackpad, you can also hold down the Option key and scroll up and down to zoom in and out. Now I want to focus on just this particular piece of data, the activity right here, where I was scrolling. And to do that, I'm going to apply a filter. And that is just a click and drag. And it selects just those specific samples so I can focus on that particular data. Now I'm going to create a little more space down here. Now down here, this is our detail view. What this is showing us is the percentage of time profiler samples we have inside of a particular function or method, and then the symbol name. So here is our percentage, and here's our symbols. And now the first thing you usually do when you time profile is you start expanding these out, looking for kind of comparing the numbers over here with the specific method over here or function, looking for things that kind of stand out as, jump out at you as something that's worthy of investigating. Another option is if we go over here to our inspector pane and click on the extended detail, we immediately see our heaviest stack trace. And this is for our main thread. So this is where focusing here is where I'm going to get the most bang for my buck when I'm doing time profiling, trying to make performance improvements. So let's take a look at what this is doing. The main is calling application main. We're getting a run loop. There's some core animation work happening. Here's a context draw path. There's not anything here that really stands out as something that seems out of the ordinary. And in fact, this is actually a really common occurrence when you're profiling. You're looking at what is your application doing the most? Well, it doesn't look like it's doing anything special. There's no call to compute the 40th Fibonacci number in here or something. However, looking at this call stack or the stack trace, there is something I know what my application does. It's a really simple prototype app. Really what it does is it builds a path and it draws a path. And I can actually see in here that there's a call to CG context path. It's not being called by my code according to this stack trace, but it is here. It is taking up a fair amount of time. So I'm going to go ahead and click on that and take a look at it. And if we go ahead and look back at our call tree, now I actually do see something interesting here. What we have is the draw path, according to this call tree, is being called by this draw layer method on UI view. And that is also calling our draw rect. This is the draw rect for our graph view. And I expect that to take a fair amount of time, because that's one of the things my app does. If I go ahead over here and look at the time, context draw path is taking up, it's in 55% of the samples, but my draw rect is in very few. This is interesting, because if I double-click on my draw rect method, it will take me to the source code. And I can see, if you look down here at the bottom, I actually do call draw path from my draw rect method, but it's not showing up in any samples. Everything in here is an add path. This is unusual, especially since kind of my expectation is my own draw rect method would take a while to run. It's basically half of what my app does. And looking at this, I actually noticed that, well, drawRect returns a void, and context drawPath is the last method called, and this is probably a case of what's called tail call elimination. And to tell us more about tail call elimination and how we can verify that, I'm going to send it back to Chad.
Okay, so to explain the situation that Chris is seeing, we have to first understand a little bit about how the time profiler sees what's calling what inside your application. Now, this is going to get a little technical, but I'll try to walk through it step by step. So on the left here, we have our code for drawRect. And on the right, we have what you would imagine the stack to look like for that thread right before UIKit calls into our drawRect. Now, when that call is made to our drawRect, it will do what most functions and methods do, and that is to establish their own call frame. And that starts off by first pushing the return address from the link register and the previous value of the frame pointer onto the stack. So now drawRect knows how to return to its caller and restore its frame pointer. Now, the next thing that happens is we take the frame pointer and we set that up to the new base. And then drawRect will make room for its local variables in its compiler scratch space, and that's what now we have a frame for drawRect. Now the code starts to run. Eventually we come down here to drawPath. And drawPath does the exact same thing. It pushes its own frame onto the stack. Now the way Time Profiler works is it uses a service in the kernel that will sample what the CPUs are doing at about 1,000 times per second. And in this case, if we take a sample, we're going to see that we're running inside context drawPath. And then the kernel can look at the frame pointer register and see where the base of that function's frame is and find the return address of who called it. So now we can see that drawRect called into drawPath. Now if we want to find out who called into drawRect, we can use these frame pointers that have been pushed on the stack to find the base of drawRect and then continuously go back through the stack until we hit the bottom. This is called a backtrace. Now, if we take enough of these and we put them in the call tree view, you can actually get a pretty good picture of what's going on inside your application. Now, I want to point out here that the frame pointers on the stack are absolutely required. So if you're compiling your code with fomit frame pointer, you're going to have to turn that off if you want to try to do the kind of time profiling that we're doing. Now, let's look at the optimized cases. This is where drawRect has been compiled with compiler optimizations enabled. Same situation, we have a drawRect frame. We're about ready to call into drawPath. But you'll notice that once drawPath returns, drawRect is finished. Doesn't need to do anything. So it's going to return. And the way it returns is it pops the stack frame, it restores the previous value of the frame pointer, and it jumps back to its caller. Now, the compiler will look at this and it'll say, well, why does drawPath need anything from drawRect's stack frame? It doesn't. And furthermore, why come back to drawRect at all when it's just going to return to its caller? So what it does is it rearranges the code like this. It's going to pop the stack frame, restore the frame pointer, and then make a direct call back into drawPath, which means that we don't need to do a jump back to our caller. Now, that's harder to explain than it is to see. So let's just imagine what it would look like when we run this code. So we're going to pop the stack frame off. That gets rid of the local variables. We're going to restore the frame pointer to its original value and the value of the link register. And then we're going to jump into the beginning of the code for drawPath. Now, drawPath is going to push its own frame back onto the stack using the value that it found in the link register and the frame pointer. So from drawPath's perspective, it was called directly from drawLayer and context from UIKit. Now, if we take a time sample at this point, we're going to see the exact same story. So even though that's not the actual call sequence that happened, this is what the time profiler saw. So that's what we ended up seeing in our call trees. Now this is called tail call elimination. It's very common in highly optimized code, and it has a few benefits. First, it saves stack memory, and in the process of saving stack memory, it keeps the caches hot. So we're reusing the memory that reuses the data in the caches. Now it has a much more profound effect on recursive code, specifically tail call recursive code. And that's where a function or method calls itself as the last thing and then returns. Without having to push those frames, a tail call elimination inside of a recursive function can make the performance just as good as its iterative version. Right? So you don't get the stack growth and you get the high performance as well. So this kind of optimization you'll probably want to leave on if you have highly recursive code. Now, if you want to turn it off for the sake of profiling to show a little bit cleaner stack trace, you can turn it off by going into the build settings of your project and setting the compiler flag, the C flag, to fNoOptimized sibling calls. Now, that'll turn off the optimization and, unfortunately, the performance gains that go with it, but you will get better results in the time profiler. Now, if you choose to live with it and you just want to identify if a tail call is happening, then what you can do is you can look at the disassembly and look at the call site of that last call. Now, if it's a normal call, it's going to use a branch and link family of instructions. That's our first example up there. And what that does is that jumps to the new function and then also saves the return value in the link register. If it's a tail call case and we're going to jump directly into the new function, then it's just going to be a direct branch instruction, so without the BL. On Intel, that would be a call instruction for your branch and link, and your branch would be a jump instruction. So if you see it in Intel disassembly, it looks very similar. So now it's up to Chris if he wants to disable the optimization and recompile, or he can carry on. So Chris, your choice.
Thanks, Chad. So I'm just going to go ahead and take a look at the disassembly. In Instruments, up in the upper right-hand corner of the detail view, there's a little button. It's View Disassembly. If I go ahead and click it, I can see the disassembly for the method here. And we can, in fact, confirm the call to context add path is a branch and link. The call to context draw path is just a simple branch. I am confident that this is a case of tail call elimination. That 55% that I saw on the call tree that was not attributed to my draw rect actually should be attributed to my draw rect. So this is actually really good news. Now I know my draw rect is on my heaviest stack frame, my heaviest stack trace, and I know it's consuming 55 to 60% of my time. So this is great. I know where to optimize. I optimize draw rect. I am good to go. So let's take a look at this draw rect. Looking at this draw rect, if I had a table, I would flip it. There's not much to optimize here. It's hard to think of a simpler draw rect that actually is functional. We have 4 function calls, context, CG calls. This draw rect really does not do much. And it turns out this is actually a really common occurrence when you're doing profiling. You'll take a look at your hotspots in your code, and there's actually not much you can do in your code directly to improve your performance. So at this junction, what do? Other than flipping tables and maybe crying into your pillow at night, what we did is we went through and we started looking at the core graphics documentation and other drawing, Cocoa drawing documentation, and we came across this particular property right here. This draws asynchronously. Lo and behold, thankfully, some anonymous Apple engineer created a Make My Code Faster button. This is excellent. And right above it, you can see I've copied out a bit of the documentation and pasted it in there. It says a couple things that are interesting. It says, first of all, that it may improve performance. It may not. And you should always measure. So, I'm kind of like, OK, Dad, let's go ahead and measure. Let's see if this actually improves in performance. So this time to start instruments, I'm just going to do Command I for instruments. And it's going to do the same thing. It's going to build the application, install it on the device, bring up the template chooser. And it takes just a moment, 2 moments, 3 moments. Here we go. Now, another shortcut I like to use is if you take a look at the Choose button down here, if I hold down the Option button, it changes to Profile. And what that means is as soon as I click this, the application is going to start recording. So it saves me a step or two. I'm going to go ahead and do that now. Now, Time Profiler is going to come up. This is measuring my app. I'm going to just do some quick scrolling back and forth, capture a little data. I think that's enough. Let's go ahead and stop the recording. And I'm going to filter to specifically my scrolling data. If we go ahead down here and look at our detail view, this looks really promising. You can see there's multiple threads here. The threads are doing work. That's really good. If we go ahead and, if I hold on Option and click the disclosure triangle, I can see what this thread is calling. There's some dispatch calls and some CG calls, so that's good. This is my drawing code. We'll go ahead and check the other one just to see. Whoop, hold on the Option key. It's the same thing, dispatch and some CG calls. So this is really good. This looks really promising. I'm now multi-threaded. In theory, my app is faster. However, multi-threading does not necessarily mean faster. We really should confirm that this is actually doing anything for us. And one way we can do that, I happen to know this device has 2 CPUs. If the CPUs are operating in parallel at max capacity, I should be seeing a 200% CPU usage in my graph up here. I'm not seeing anything over 100%, so that's a bit of a warning sign. It doesn't necessarily mean that they're not both doing work at the same time, but it means I need to check further. How can we check further? Instruments has what we call strategies. It's different ways of partitioning your data and taking a look at them. There's 3 of them. The first one is the instrument strategy. It's the default we're looking at here. The second one is the CPU strategy. It shows your data per CPU or CPU-relevant data. And the final one is the thread strategy, and it shows you details about what each thread is doing. So let's go ahead and take a look at the CPU strategy. And we can see now we have each of our CPUs. We can see how much work it's doing. And then down at the bottom, we can see the combined usage. Something to do here, when I zoom in far enough, the details, what the graph shows me, will actually change. Instead of showing me the average CPU usage, it's going to show me whether a CPU is active or not. So you'll see it change from average usage to either on or off. So now each CPU is showing either an on state or an off state, whether or not it's actually working. And what do you notice here? The CPUs are never working at the same time. There's actually no parallelism here. So, this is not good. If we want to feel even worse, we can take a look at the thread strategy. And what this is showing us, each of these icons represent a sample that Time Profiler took. You can actually click on it and see the call stack. So here, this is on one of our background threads, and you see this core graphics calls. Up here is our main thread, and you can see our main, the work we're doing on the main thread. And as you can see, if I zoom in to the right level, which is probably right here, and I scroll around, you can see there's not really anywhere where 2 threads are working at the same time. It's pretty much jumping from one thread to another. So, the draws asynchronously has actually not really done anything for us. In fact, in theory, it may have even slowed us down. Because now, not only are we doing the same drawing work, but we're also managing, Core Graphics has to manage the threads that it's working on and that sort of thing. So that didn't really help. I'm going to go ahead and turn it off and flip another table, I guess. It's not clear. Our magic button didn't help. What do we do now? And this is actually a really common occurrence, again, in time profiling. You try lots of things. Most of them don't work. So we step back. What does our app do? It builds a path, and it draws a path. Well, we've seen the draw path code. Let's think about the build path code. And that's actually right in here. So what we wanted to do is we wanted to investigate the actual path we're building. And what this code does is it just loops through our data elements, creates a path, and adds a line to that path for each data element. And we want to know how many lines are we adding to this path. Well, this is something actually that Time Profiler can't tell us. It can't tell you how long or how many times a particular method or function has been called. It doesn't know the difference between a slow function that's called a few times or a fast function that's called a lot. So in this case, we resorted to our old friend NSLog, and we just have a thing. Every time we add a path, we increment our counter, and then we log it when we're done with the loop. Something important to point out here is NSLog is not a very fast function. You don't want it in high-performance code. In fact, you probably don't want it. You don't want to use it for anything other than for gathering diagnostic information or debugging. So when you're done, delete it from your code. In this case, we just commented it out so you could see it. And what we found is that we are adding 10,000 lines to our point in cases where we did not need to do that. In fact, there's no way to display 10,000 lines on this device, especially when you're zoomed out far enough that all the data fits within 100 screen points. There's no reason to draw 10,000 lines in there. We just need to draw 100 lines. That's a lot less work. So we went ahead and we created an implementation that did that. If multiple data elements, data points, are within a single screen point, it just finds the max and draws a single line. So if we only are using 100 screen points, we're only creating 100 screen lines. So we're going to go ahead and switch to that implementation. And we're feeling pretty good about it. I'm going to go ahead and change our element count up to our goal of 100,000 instead of 10,000 and see if that helped us at all. I'm going to use Command-I to start up instruments. Since instruments is already open, it's just going to bring it to the foreground, and it's going to start recording immediately. So here we go. It's doing a new recording. I'm going to go ahead and scroll. The scrolling seems fine. I'm going to go ahead and zoom out. The zooming performance is much, much better. Takes longer because I've got more data to zoom out, but that actually looks pretty good. And I'm going to do the swiping back and forth, and it's tracking my finger really well now. It's actually keeping up with it. It's doing a fantastic job. Hooray. All done. Except not quite. If we look at the actual amount of CPU we're using while we're scrolling back and forth, we can see, sometimes it gets down to 60%. It's usually in the 70s or 80s. Technically, we're meeting our performance goals, but what are we going to do? What's the very next thing we're going to do with this app or with our prototype? Is we're going to add additional features. And we know that we need more headroom than what we have here. Right? So how can we make this even faster? How can we give us a little room to make our app better and still meet our performance goals? So let's go ahead and focus on this. We're going to filter to that data, and I'm going to give myself a little room. In this case, I'm going to just hold down the Option key and click Main and expand this out. And I can actually go down here and I can see this method here. Now that our drawing of the path has gotten fast enough, it's our building of the path that becomes the bottleneck. And I want to focus specifically on this method. I'm going to click the Focus button. And what that does is that just moves aside everything outside of the method and then normalizes our times, our percentages to within this method. And if we close up some of these, we can see that this method is spending 55% of its time in our getNext element, and it's spending 10%, 11% of its time in obj message send. Now, something that I know is that obj message send is very fast. It's a really fast method. It's super optimized, but if I can get that 10% back, I want it. And if we actually go ahead and take a look inside of our code here, we can see it's actually very clear. Most of our time is spent on obj, or is spent on getNext element. And this percentage here is a little higher than it was in the tree view because it includes the obj message send time. So clearly, if I can get rid of the obj message send and I can make this iterator faster, I hopefully can get the performance boost that I want. And to give us some ideas to how to do that, it's back to Chad.
All right, let's talk about obj message send for a second. Now, obj message send, you guys may have seen it before. It implicitly gets inserted by the compiler whenever you use the square bracket notation, or whenever you use the dot notation to access a property on an object. And its purpose is to look up the method implementation for that selector and then invoke that method. So that's a long way of saying that's how we do dynamic dispatch in Objective-C. Now, obj message send is extremely fast, and it does not push a stack frame. So when you're looking at your time profiles, typically you won't see its effect. Now, the times that you do see it would be a perfect example like we have, where we're seeing it in our iterator, because what we're doing is we're iterating over 100,000 points, and we're calling the getNext method, which has a very small method body. It just increments a couple values and returns a structure. So what's happening is all of that overhead time from the Objective-C message send is starting to accumulate into something that becomes measurable. Now, is there a way to get around that overhead? And not exactly. So Objective-C by design is a very dynamic language. So you have to make the Objective-C message send call when you're accessing methods for objects and classes. Now, it does this every time because you can even switch out method implementations at runtime. So there's no compile time optimization in Objective-C that could say, well, I want to call directly into this particular method body. The only exception here is if you do what's called method caching. And that's where you look up the method implementation yourself and you call it through its function pointer. Now, in general, I don't recommend that you do that. It's a little fragile, as you can imagine, but in general, in my experience, it hasn't given me the kind of performance wins that I'm expecting. Because you got to think about why we're here in the first place. The reason that we're here is because the getNextElement method has a small method body. So even if you invoke it through its function pointer, you still have to marshal the arguments and push the frames onto the stack and pop them when you're done. That's exactly what you saw in the previous set of slides. And that can be a lot of overhead when you're just doing an increment and then return. So I wanted to just make sure that I pointed out that method caching is not as fast as inlining. Because what we really want in this case is we really want that small method body to be inlined. So how do you do that in Objective-C? Well, you have some alternatives. The first one is you could have used C, and you could have used structures instead of an iterator. You could have passed a C array into our method, for example. Now, if you want to keep that OO flavor, you also can use C++. Now, the way you use C++ in Objective-C is you rename the file from a .m to a .mm, and then you can use C++ syntax. And because Arc is usually on by default, you can take Objective-C objects, and you can put them in STL containers. You can even put them in instance variables on your classes and structures. Now, this is very handy, and you get all the performance benefits of C++, and I've used it extensively in instruments to get as much speed as I possibly could out of the track view and a couple other critical areas of instruments. Now, I also know from firsthand experience that there's a major downside to this, and that is you have to know ahead of time which parts of your code are going to benefit from C++ and which parts of your code are going to benefit from Objective-C. And sometimes, until you get to doing some profiling, you can make a mistake there, as we did in our demo case. We wrote our iterator in Objective-C, not realizing that it was going to eventually show up in one of our time profiles. So is there a better alternative than what I just mentioned here? And there is. Come on, you knew it was coming, right? So Swift is actually ideal in this particular situation because unlike Objective-C, it's only dynamic when it needs to be. So if you make sure that your performance-critical classes are internal and you use whole module optimization, the compiler can actually, or the whole tool chain, can determine when there's only one method implementation, and it can inline it right into the call site. And that will give you some significant wins, especially in our iterator case. Now, because we are still prototyping, rewriting our iterator and our view controller in Swift is actually pretty easy, and so Chris has done that.
Thanks, Chan. If you were paying close attention to the code in the project, you know I have a Swift implementation ready to go. This is actually a really straightforward port of our Objective-C implementation with a couple of the suggestions that they made in this morning's session about improving Swift code, specifically turning on whole module optimization. So let's go ahead and profile this. I'm going to do Command-I. It's going to build, install to the device, and it should just start profiling. Okay, and I'm going to bring the application forward so you can see. Here's the scrolling. Scrolling looks really good. I'm going to zoom out. Oh, if I can manage. There we go. Zooming out. It stays nice and fast. It's a lot of data to zoom out of. And now, if I go ahead and move back and forth, it moves really fast. It's very nice. Thanks. And actually, we can go ahead in here and take a look at what our CPU usage is. You know, we've got actually further improvement than we were expecting. We were expecting maybe 5 or 6% improvement just from removing the obfusc message send. This is actually a little lower. And I can actually, if I turn down this disclosure triangle, you can see the two runs next to each other. And you can see the previous run and the current run. And the current run is clearly much lower. And actually, if I go ahead and go in here and look for my build path method, I have to search for it now. Oops, that's actually not how you do a search. If I hit Command F, it's going to bring up this dialog here. And I can type in build path. And it's going to show me my method here. And if we take a look at this, we can see here's my Swift code. My get next call, which is actually right here, isn't showing up in any samples. No samples landed on this. And why? That's because Swift was able to actually inline it, which means that there's no function overhead, no method call overhead whatsoever. And because the code for the iterator is inlined with the rest of the code, it can make even further improvements, which explains how we got even better performance than what we were hoping for, just from skipping the dynamic dispatch. OK. Chad, you have anything else you'd like to tell these nice people?
Of course I do. We got like 5 minutes. OK, so a couple tips here for you to explore instruments on your own. First one I wanted to point out is under the recording settings. It's called record waiting threads. Now I mentioned that the service in the kernel we use samples the active CPUs, but if you have threads that are sitting around blocked on a lock or waiting for I/O, you can check this checkbox, and the service will sample those idle threads as well. So if you have code that's contending over a lock, you'll see those hotspots show up when you enable record waiting threads. Another thing that I find interesting is to enter the display settings in the call tree section is invert call tree. And figuratively what that does is it flips the call tree upside down. So instead of seeing the leafs at the bottom nodes of the tree, so these are the functions that don't call into anything, they appear at the top. So if you have a utility function that's being called from 5 or 6 different places, you might want to invert the call tree so that you can see who's actually calling into that particular function. So it gives you a different perspective on your data in the call tree. Now, when you right-click a node in the call tree, you also get a context menu, and there's some interesting stuff under there as well. One of the things that I use from time to time is the charge to caller. So what you can do is you can charge a function or a method to its caller. You can also charge an entire library or framework to its caller. And there's an option in there as well to prune a subtree. So if you don't want to work on a specific problem at the time, you can just prune that subtree out of your data and focus on what you want to focus on. OK, so what did we learn? So through all of this, one of the first things I wanted to remind you about is to incorporate performance targets early. If you're doing a big performance rewrite like we were, start with a budget and keep monitoring it, because once you start layering a lot of code on top of that, it's going to become a lot harder to change. Secondly, always measure. Through all of our demonstrations, we were taking time profiles with the time profiler. We were using that data to find the hotspots, and then we were tuning it. And then by the end, we actually had a very well-performing application. If you go in blind, depends. I mean, you may get lucky and hit it, but I would start with a measurement and go after that first. And the third one, this is most important to me, is I want to encourage you guys to keep digging. Some of these performance problems that you look at first might have seemed impassable. You might say, oh, that's happening in someone else's code, or that's a side effect of the runtime. But the reason that we gave you all the details on how the time profiler works and how the runtime works and what the disassembly view looks like is we wanted to show you that there's this whole other world out there of more details. And by using some of that, you can solve the kinds of performance problems that we were solving today. So I encourage you to keep digging, and with a little creativity and going out there into sessions like this, I know you guys will be able to fix and hit the performance targets that you want. So that about does it for today. Stefan Lesser is our DevTools evangelist, so if you have any questions or feedback, please contact him. We have a few related sessions, energy debugging issues. Turns out that if you have efficient code on the CPU, it's also going to use less energy. So there was that session on Wednesday. Also tomorrow, there's performance on iOS and the watchOS. Good news, the time profiler can target apps on the watch, so that's a big boon. And enjoy the rest of your conference.